Hi, everybody. I'm Robert Burke. I am a Googler of some number of years working on the Google Cloud Dataflow team. For the last most of those, I've been working on the Apache Beam Go SDK. Very recently, at least it feels very recent, I've been made a Beam PMC member, which is why I decided I'll stick with my Apache address for these slides, because why not, instead of my Google address. But what I have been working on for the last 2 and a bit years now has been a new local runner that I call Prism. And so welcome to the deep dive on this runner. So what the heck is Prism? To start, it is a local portable runner. It is an Apache Beam runner, and it is portable only. So unlike with the direct runners in the Java and Python SDKs, it always uses the portable mode of execution. If you don't know what that is, I will describe it in a little bit more detail later. But it's local in that it always runs on your machine directly. The data is currently stored in memory. It's always the same machine. It is not distributing your data or processing across multiple machines. Currently, it is built with Go, largely for its standalone compact binaries and its powerful concurrency primitives. And largely because I originally wrote it for the Go SDK to replace its direct runner. So we're going to start off with a light demo here. So unlike the other direct runners or local runners, Prism has the ability to produce a little bit of a tiny web UI. You can access it at whatever the web address you set. In this case, my localhost port 8074. Due to the current setup, I'm not going to show a lot more code or command line stuff. And because I was hoping to have the next Beam release out to make it a little easier to show these particular features for submitting jobs with Java and Python, instead, you'll have to be satisfied with me submitting the full test suites of the Java and Python validate runner tests against the Prism binary that I've got stood up here. There's not a lot to see on those because they are just single command line invocations with Gradle and with a Python. But we should start seeing jobs starting to spin up. So this is a particular artifact of how Python is running tests in this case, in that it doesn't actually set a name for any of them presently. I'll probably fix that for the next version. But as you can see, it is getting in a pipeline graph of information, currently set up as a table of data, along with all the various little metrics that are produced, at least in terms of these small scale tasks. So we get the number of elements, how long various profiling metrics take. None of these will probably show more than 0, frankly, because the sampling size will be smaller than that, as well as general key collection element counts. So it's not a lot to look at, frankly, but I wrote this to help debug what was processing while I was developing Prism. But it's a start for making a more interesting local runner experience with a far better local graph UI and similar. So have to be satisfied with the engineering UI there. Oh no. We'll come back to that because Java will take a little bit of time to compile because I had to unstash some changes. That is my fault. But in the meantime, back to the slides. So a little bit of history and the rationale of why I built Prism in the first place. First, there was the Go Direct Runner. This was back in 2016, 2017, when the Go SDK was just starting. We needed all the other languages, Python, Java, had their own little direct runners in order to do some local testing. The Java one had become more and more elaborate because it was where a lot of features were developed first. And this is just where you would develop those features first. The Python one, similarly, there was a larger team working on that. The Go team never had a large team working on it, so it has always perennially been a little bit behind. And because the Go SDK by itself was developed for certain uses inside of Google, we would use the internal equivalents of Dataflow in order to run the pipelines. So a lot of the features were then built and developed against that runner, which meant that our direct runner languished. Ultimately, this turned out to be a fairly big problem with respect to adoption for the SDK itself. I made this particular observation a couple years ago that if the default runner of your SDK is unable to support a feature, then users will think that the SDK doesn't support that feature at all, even if it will work on Dataflow and Flink or internally on the Flume runner. So it became a kind of a learning impediment and to people adopting the Go SDK. So because even though the Go direct runner could do a bunch of things and you could write a fairly large variety of pipelines, it had other issues. It didn't have state, it didn't have timers, it didn't have triggers, it didn't have windowing strategies. It cannot do cross language. It also had various other bugs in that, like, it was too permissive in what kinds of pipelines it would allow, in that certain idiosyncrasies of how we needed to design the Go SDK required extra bits of boilerplate that weren't required or necessary for the direct runner to execute, but would cause the pipelines to fail when you tried to use it on a bigger runner like Dataflow or Flink. It was basically too easy to write pipelines that would just not work. Eventually, I decided I had had enough of that. So around late 2021, I started iterating on what a portable version of the Go Direct Runner would look like. It was like using the Beam Portable APIs, and because that would avoid some of those category problems in terms of you could write a pipeline that would then not work on Dataflow or similar. And as a member of the Dataflow team, that is kind of a big concern. I started iterating this as a personal project. It was in my little personal repo, starting in January 2022. Eventually, only a little bit more than a year after I started really working on it, made it into the Beam repo for 2023 and made it fully the default for the Go SDK in July of that year, in time for Beam 250. It's like a particular watershed moment for me on why this was really necessary, because I was only iterating it a little bit in my own personal time, was in summer of 2022 when I was giving a talk at GopherCon Europe for a talk called Stream Processing End-to-End, because we had just added all these streaming-able features to the Go SDK. We started adding state, we had trigger support, we had all these fun things that we couldn't execute locally. So that talk goes very well in depth for how the watermark works and how triggering semantics work, but I couldn't show anything off on how you would actually validate that your streaming is working end to end. The last two Beam summits, 2022, 2023, I gave other talks about Prism, kind of marking the progress, noting some of the needs and kind of foibles with direct runners generally. But with the 2.5.9 release that is in progress right now, Prism will be available to the Java and Python SDKs. So progress has very much been made. So bear with me for a moment, because as this is a deep dive, it will go into the kind of a little bit of how the code is organized, and that's what this section is. But so you can understand that, this is kind of the Beam portability model in a nutshell. Beam abstracts processing over SDKs and runners, putting a clear divide in responsibilities between what the user needs to write and what the actual execution engine needs to implement in order to support that. This allows us to do fun things like being cross-language, but also for us to be able to avoid a combinatoric explosion as we are trying to support different SDKs on different runners. So an SDK would take a pipeline, submit it to a job management service that the runner provides. That runner would then start executing the job. Depending on how that that SDK was, or that pipeline was configured, the runner will start communicating with will start initializing different components in order to present workers for it to actually execute the SDK's work and actually run the various parts of the user code. Whether that is in the workers are operating in loopback mode, calling back to the same process that launched the pipeline in Docker containers, wherever they may live, or in literally sidecar processes. All of these are kind of communicating over gRPC connections through a couple different services that we have for what we call for portable Beam. Mainly the job management service that accepts jobs and reports on the status of jobs of pipelines, and the Fun API, the function execution framework, really, if you want to go full on, that coordinates and shows how the runner coordinates execution of workers and produces or tells the SDK what work to execute. So with that in mind, Prism is relatively small in terms of the amount of code that is needed, because it is leveraging a little bit of stuff from the existing SDK, largely coders in that respect. But it has a couple of different job-based packages for whatever tasks that it needed to do. In the root directory, we have literally the main entry point, prism.go. But then there's no other immediate sub-packages aside from the internal package. An internal package in Go is very much the most private package that you can get. Only things in the root directory that are the root parent directory of the internal package and siblings of the internal package may use things that are deeper in the internal package. This is very useful for being able to be quite certain that nothing else is depending on this code, so you won't be worried about making breaking changes that you're not aware of, which is a small risk when you are developing in open source, because eventually someone's depending on every possible line of code and permutation of things that you might be writing. Within the internal package itself, there's a bunch of code that exists largely for managing the job executor, how we handle managing stages, and pipeline pre-processing to generate those stages. And then a mere 6 packages for different little subtasks. A config directory for managing a configuration facility that we aren't currently using, so I won't talk about that a lot. The engine, which is the real heart of Prism, which handles watermark tracking and calculations, manages all the data elements, and the various state for any of the stages that we are executing. Job services, which is where the Prism's front end for job management lives, so that hosts the actual gRPC server code and how that all integrates. Earns, honestly, it's mostly because I liked having a small package name earns before any of the earns. Otherwise, this could have lived anywhere. The web for showing off that UI I demonstrated earlier, and worker, where the actual Fun API coordination happens, which actually communicates back and forth with the SDKs. This came about largely because of this particular design came about through organic evolution, because I'll just read this particular quote. A simple system may or may not work. A complex system that works is invariably found to have evolved from a simple system that worked. A complex system designed from scratch never works and cannot be patched to make it work. You have to start over from working from a simple system. All of this came about largely because I started writing a for loop to process data in batch because I needed something that was better than the existing Go SDK or the Go Direct runner. And it moved on from there. So with that in mind, as Prism has developed, care has been taken to kind of limit how certain things are interacting. Things to call out here are basically where the protos actually get used. Notably, in the engine package, which handles watermark tracking, the actual stage state, timers, so on, does not actually depend upon any of the Beam protocol buffers. Largely because I wanted to avoid specific coupling between how we're communicating these aspects across SDKs and so forth with the actual engine. After all, Flink, for example, does not implement things in terms of the Beam protocol buffers, and yet it can quite readily execute streaming pipelines, job services, so on and so forth. Now we're at the meat of the talk for how the actual big loop works, because ultimately what it comes down to in order to execute a Dataflow pipeline, a Beam pipeline, it's a matter of iterating until the watermark for all stages has advanced to infinity. But before we quite get to there, we need to see how we actually get to the point where we can start evaluating what the watermarks actually are. So in the internal package, in what I call the job executor function, we first pre-process the pipeline into various stages. This is combining and fusing transforms together that are compatible in certain ways and can be executed simultaneously or not, or in sequence. Ultimately, we end up with this produces the metadata required for executing a given stage and which transforms are involved in those stages. Stages turns out not to actually be a term we use specifically in any of the Beam definitions, but it is what is kind of common across most of the runners for what we're talking about of the results of these optimizations we do on the processing graph. From that, we actually create the actual stages that we use to mention the metadata. These are static metadata. They will not change over the lifetime of the job. This is information like whether the stage itself is stateful. It represents an aggregation, what timers it has, what its input P collections and output P collections are, side inputs, and so on, and its various relations to other stages. With that information, we produce workers, or at least representations of workers for each of the different environments involved. If it's multi-language, there will be multiple environments involved. And start configuring the actual stateful analogs of those inside the element manager. After that, the job executor actually starts processing bundles. It requests bundles from the element manager. Each bundle produced by the element manager is keyed to a specific stage. Each stage can execute independently, and this is largely all the job executor does until the job either reaches a successful termination or encounters a failure. Each bundle is taken from the queue that we've produced and sent off to the appropriate SDK worker or processed locally in memory if it is a runner side transform, like a group by key, for example. This is a small microcosm of what the Fun API does, but its main load-bearing component is the process bundle request and process bundle response, along with the state and data channels along the side to produce or provide data to the SDKs for it to process based on those the descriptors in the process bundle request. Once all of that is done, the response is returned back to the runner. If it's successful, we persist the results, full data, the current state, metrics, back into the element manager. If it fails, we report that failure. currently, as Prism is currently is not designed for reliability and not presently designed for like durability and reliability. It doesn't do retries. So reporting the bundle failure isn't the most important part here, but in the future, that would be how we would report data that a specific process had failed, and that data should be reprocessed if necessary. Once the bundle is complete, it returns back to the job executor loop, and another bundle starts iterating around. Otherwise, in bundle failure, we just fail the job. Because Prism has its origins in the Go direct runner, one of the useful things for a direct runner is to be able to unit test reliably and be able to root out flaky behavior from your code. So having fast fail semantics, such as killing the job entirely as soon as we encounter a failure, helps you route out those particular kinds of failures. Let's quickly just check to see if the Java SDK decided to finish. It did. So scroll down. Java, on the other hand, does produce a bunch of test names. And similarly, you can see it's producing metrics, performing counts, summing sizes, and so on and so forth. Okay, so about time. Central to any Beam pipeline's execution is the notion of a watermark. And unlike an SDK, which kind of treats a watermark as a side concept, that it's not even metadata that it has explicitly. It's data that is derived from whatever it has produced. A runner itself actually has to calculate and determine the watermark for each stage in order to be able to produce bundles as time goes on. This slide contains a lot, but it is as compact as I could make explaining how a watermark is actually calculated. So for a given stage, there is the input watermark, which is whatever has been produced as the output watermark from any upstream stages, and its own output watermark based on its current data. We calculate the watermark in a iterative process, essentially. As the stage has been marked for that its state has changed, whether that is based on the new inputs that are pending for it to process, or new timer holds, or estimated outputs from a previous process. We use that information in order to actually calculate what the watermark is. In this case, it is, I'm not going to try and read the little bit of the formula off to the side there, but it takes all of these facets into account in order to have a monotonically increasing watermark. So we know where the event horizon of the data is. The future is always kind of descending through the processing graph as as elements are flowing through the pipeline. And it is this kind of constant push towards infinity that allows the bundles to begin executing. In this case, once a stage has no more elements, by default, it's already at infinity if it has no other modifiers to how its watermark will be progressed. So an impulse, for example, the impulse stage has no inputs itself. It produces a single element, which starts at negative infinity. Once that element is sent down to its consuming stages, its output watermark is now at positive infinity. And thus we need to notify that the stage itself needs to, or that its consuming stages might need to update their own watermarks. And this process kind of iterates and continues. All that work is done in the element manager in the engine package. We track the state for each stage, which contains all the pending elements and their various bits of metadata. We derive the watermarks based on that data. All the stages are also evaluated for bundle readiness based on their current watermarks. And the element manager ultimately is responsible for actually dividing whatever pending elements are available for processing into bundles for processing by the execution engine or the job executor function. I tried to make a nice little staged view of this chart here, which goes through the bundle generation loop, but I couldn't quite get it to work. So unfortunately, we'll have to bear with this for the moment. Bundle generation in Prism is currently very single-threaded. There's a single Go routine that is actually checking to see which states need updating, going through, checking each state or stage based on their state, and then seeing if that state or stage is able to produce any elements. Stages tend to be marked for evaluation only when some parent transform, upstream transform, has pushed additional data down to them to provide new pending elements, or when a bundle that it has processed has successfully finished, so old elements can be removed from the pending state, or other timers have fired, whether they be processing time or event time. Prism's deployment is currently, if in the Go SDK, it is just built into the SDK itself. So in many respects, it is like the direct runner it originally came from, and like the direct runners in the other SDKs. But it is still, while it is inside the same process as the Go pipeline when running like that, it is still running with all the portable mechanisms, using the gRPC services, starting up loop back workers internally, still needing to do serialization and so forth. For the Java and Python SDKs, we're using pre-built binaries that are built and pushed out as assets as part of GitHub releases. We've been experimenting with that a little bit since 2.5.7. We built a variety of them, sign and hash them for validation or for verification for Linux, Windows, and Mac for both ARM64 and AMD64 platforms, because we're leveraging Go's ability to cross-compile to various target platforms. With the upcoming 2.5.9 release, if you use the Prism runner, it will automatically download the version paired asset for your machine architecture and operating system, and start that process and start running your pipeline against it in loopback mode, so that it will communicate, the runner will communicate back to the SDK process. Some surprises as we were going through developing Prism to this point. SDKs are way more permissive than I expected, partly because I've been deep in the Go SDK side, and in my mind, having something that is too permissive makes it too easy to make mistakes, too easy to think certain other things are working. So the Go SDK by itself, for various reasons, needed to become fairly restrictive in what it permitted. And Prism was originally developed with those kind of guide rails in mind. Things I didn't know about until I started dealing with the Java and Python SDKs and making Prism work for them was that SDKs turn out to be able to pre-optimize pipelines. This happens for the Python SDK in that it will do combiner lifting and split out splittable do funds if necessary before submitting a pipeline to the job management service. So Prism needed to be tolerant about that because it can still execute those optimized transforms. Composite transforms as well may be empty entirely, but still technically be part of the graph. They have no particular transforms, or maybe they're doing a different view on a P collection, which isn't actually a transform as it turns out. Those sub-transforms and composites may have entirely non-standard beam or like non-standard erns that only they know or care about. So Prism shouldn't care about them either. In terms of general beam things, turns out flattens are allowed to not have any input collections at all. There is an actual good use for this though, having optional side input data. But the important thing to note is that we need to end up treating a flatten in that respect kind of like an impulse, in that it needs to be set to infinity and be able to not block the transforms that are depending on those side inputs. Similarly, flattens also can have distinct coders for all P collections involved. I personally don't understand why you might want to do this, but there are validates runner tests that I will eventually figure out how to get to work for Java. In my opinion, the only real solution there is to add another optimization that would happen during graph preprocessing called flatten unzipping. We initially had a bunch of spuriously passing Java tests while we were trying to get the actual Prism runner wrapper working. And it turns out because at least conventionally, when you're writing Java tests for your pipelines, you use a construct called test pipeline, and then you call run. In my opinion, that run should be doing the silent blocking and stuff in there, and it probably did at some point in the past. But ultimately, if you aren't doing anything specific on your runner side or for your wrapper to block execution, that run call returns, and then the test returns, and thus it passes because it didn't experience any exceptions. So the quick solution there was to actually follow suit with what the other wrappers do in the Java SDK, which is actually have a test-specific one which does the blocking behavior. As you can see, I did fix this one. Java metrics were entirely missing, and this has to do with specific features on how Java has never really needed to run truly portably in many cases. And because Prism, I decided not to support the legacy versions of the monitoring info metrics that get reported back by SDKs across the Fun API. We only understand the modern short ID format, which is necessary for efficient processing of metrics, because it turns out having large protos reporting back metrics every single time instead of the compact payload data information, it becomes expensive. It turns out that the Java loopback mode, the external worker service as it's technically called, was never migrated to more modern provisioning APIs, which meant it never acknowledged or respected the runner capabilities that were reported by the runner over the Fun API. So I had to actually make a fix to the Java SDK in order to get this working. Moving on towards the future, the near term, the hope is to start putting Prism around the Beam site, include it in the capability matrix, part of including it in the quick starts. This is largely just to, like any of the other runners, we have these entries, not entirely everywhere across the site, but in most places. Continue adding features because while Prism is now fairly suitable for many pipelines, it doesn't quite implement everything at this time. We're still missing things like bundle finalization and on watermark expiry, both of which are necessary for the ever popular group into batches transform. Somehow we have managed to go this far and pass over 3/4 of the validates runner tests without implementing triggers at all, and various other windowing strategy bits. I have an open PR that contains more detail than this talk has had time to get into for actually producing documentation for how Prism works. Again, kind of at this medium high level that will be evergreen versus looking down at the code. And of course, a blog post on the Beam site socializing Prism more widely. My vision specifically for Prism is it gets to the point where it can become the default runner for all SDKs. That observation I had way back when, while it was very poignant for the Go SDK, is still true, for example, for the Python SDK. There are certain things that the Python's local runner cannot do. It cannot support cross-language transforms in streaming mode. It does not really support streaming mode, for example. Prism does support streaming mode and cross-language, but I haven't quite tested that to the fullest extent yet. But this is to kind of avoid that understanding gap for not just the Go SDK, but all SDKs that exist and in the future, where we have a single local runner that is quick to start up, that you can just use and not worry about any particular configuration for getting it working. Tied to this could be a possible goal to actually have a proper SDK authoring guide, which will not just teach people how to author an SDK, but also understand how a portable SDK needs to function. So that possibly I don't need to keep adding a preamble to all of my talks about how the Fun API works. Additional future work that we might want for Prism is add additional non-user visible features. There's a number of things inside Beam that you don't need in order to execute a pipeline correctly, but have been added for performance. Some of these are things that I call out in previous talks about how different runners will execute your pipeline in different ways. And while many of these things will not be user visible necessarily, they do have an effect. And it would be nice to be able to ensure that we can actually exercise these code paths one way or another very easily in a runner setting, not necessarily as unit tests. And then who knows, maybe we make it a proper single box standalone runner where you host a IP for it on some VM and you can submit jobs to it. But for that, we would need more reliability, such as durable data, and be able to handle pipeline updates and restarts, as well as a more clever splitting algorithm than what I've currently got in there. And that's my talk. Thank you very much.